Okay, minasan, konnichiwa, Zamurai Engineer desu. So in this segment, we will continue our discussion a while ago of detention member. So we're able to introduce a topic, but before we go further, since we are going to do the formula and some explanation of example, I would like to be clear if our reception is clear, including the sound. Okay. Is the sound clear enough? Please confirm if our reception is clear. Okay, thank you, Malsada, for confirming. So clear po according to Zairine. And with that, let us now resume our discussion. Okay. So very important thing, we have tension members with bolt holes. Okay, connected one member to another using bolts. So therefore, those members must have bolt holes, and it can possibly fail by fracture along that holes. Okay, at the next net section through the holes. What do we mean? It could fail on that particular area, because if you can compare the area, those areas with holes are the weakest point. Those are the weakest area. Okay, so that's why those bolt holes must be designed. There is a design on bolt holes. Okay, and this failure load may very well smaller than the load required to yield the gross section. Take note, gross sectional area. So it is different from net sectional area. So net and gross. So gross meaning the area without considering the holes, okay, or notches. So there are knots and holes and some sagging or anything that would minimize or decrease the area, because area, the material itself, would perform the necessary resistance to failure. Okay, and if the material in a particular section is decreased, therefore the material resistance to the failure will also decrease. And if the resistance to failure will decrease, therefore it is more susceptible to failure. Okay? So it is to be realized, therefore, that the portion of the member where we have a reduced cross-sectional area due to the presence of holes normally is very short compared with the total length of the member. So for example, we are connecting one element to the other. Usually those are connected in at the edge of the member, or at the middle of the member. So edge of the member, middle of the member, connect something to the bracket, connect it to the gusset plate in for example 1/3 of the length of the member, but mostly edge of the member. Okay, so very short section area compared to the total length. Okay, and through the strain hardening situation is quickly reached at the net section portion of the member. Yielding there may not really be a limit state of significance, because the overall change in length of the member due to yielding in this small part of the member may be negligible. So because the holes, the nearby area within the holes. No? It's very short compared to the total length, and computing the yield, the elongation at that particular section is very small and negligible, and therefore how can we proceed in incorporating that condition to the actual design? So we need to incorporate that so that the weakest portion of the material must be considered. So as a result of preceding information, the AISC specification, okay, states that the nominal strength of a tension member, nominal strength, take note, nominal strength. We already have a formula how to determine nominal from those other type of values, okay? So nominal, it is not a design value, that is a nominal value. You can multiply nominal value by some factor, reduction factor, something like that, okay? And so on. So we already have an idea what do we mean by nominal. So those nominal strength of a tension member, okay, is to be smaller of the values obtained by substituting into the following two expressions. So this is the specific suggestion by AISC specification D2, okay, for the limit states of yielding. So take note, there are at least three types of strength limit state, okay, strength limit state. So we have buckling, we have yielding, we have local buckling, and so on. So there are three. So in terms of yielding limit state, in the it is under the what, strength limit state, okay. So strength limit state is ULS, ultimate limit state. Actually this is yielding, but it is called ultimate. The method is ultimate, okay. So you know the difference between yielding and ultimate. So in the gross section, which is intended to prevent excessive elongation of the member, okay, so we would like to consider that at which point, at which location the member would fail, and at which point, at which section the member would experience excessive elongation. So number one equation, D2-1 equation states that the nominal strength is equal to yield stress or yield strength multiplied by gross area. So that is equation D2-1. Okay. So nominal strength is equal to, that is the main concept, okay, and multiplying both sides by a design reduction factor. So take note, if we are talking of tensile as a input, okay, as a load, okay, tension load, okay, tensile strength as a load, the reduction factor, as you can see here, okay, as you can see here, phi sub t meaning reduction factor due to tension, okay, phi sub t. So it is also read as phi. It is not. It is a little bit different from pi. Pi is 3.1416. Phi is this Greek letter. Okay, so small Greek letter phi sub t. T meaning tension. Okay? So reduction factor due to tension is equal to 0.9. This is very specific. We have to memorize this. We have to memorize. When we are talking of tension, we have to memorize that the reduction factor is 0.9. So therefore, multiplying 0.9 to both sides, so we have phi t times nominal strength is equal to phi t times yield strength, right? Yield stress or yield strength. Okay, yield stress. We have the idea that the unit is MPa when we are talking of this unit, MPa. Okay, so the unit of Pn or nominal. Okay, force, that is Newton or kilonewton. Okay, so megapascal times square mm. So the unit of area, gross area is square mm. So MPa times square mm is equal to Newton. So we usually have to divide this by 1000. That's why we can also express this as kilonewton. Okay. So then, therefore, if we are using the ASD instead of LRFD, so instead of using the reduction factor for LRFD, that is will become, we will use instead the omega t. Omega t is equal to 1.67. So for ASD method of solution, we will use omega, so t is equal to 1.67. Therefore, Pn divided by omega t is equal to yield strength times gross area divided by omega t. So we can compare using equation as the origin of this concept, original concept, D2-1. Okay. Now, for tensile rupture in the net section, okay, so rupturing on the net section as where bolt or rivet holes are present. So we have instead, take note, this is equation D2-2. This is Pn, P sub n is equal to ultimate strength multiplied by effective area. So this time, we are now using effective area. So I will just move it up. I will move the equations up. So moving it up like that. So we have two sets of equation. So the second one is equation D2-2. Again, P sub n is equal to ultimate strength multiplied by effective area. So we are here, okay? And multiplying both sides by reduction factor, take note, okay? Okay, this is again tensile reduction factor, but now we are under the rupture, tensile rupture, okay? We are on the ultimate. When we are going to use the ultimate, we have to use 0.75. Okay, that's the difference. Okay, so the difference of excuse, the difference of using the yield and ultimate, therefore, is what? The difference of 0.9 to 0.75. That is for what? LRFD. So, what is the difference of that? 0.15. So, 15%. So, usually, that is how we estimate the value of ultimate if we have the yield stress, or the value of yield stress if we have the ultimate. The difference is about 0.15 or 15%. Okay? 15%. Okay? Do you follow? So that is for LRFD. Okay, so multiplying both sides, therefore, reduction factors of T or phi T times P sub n is equal to phi T times FU or ultimate strength times effective area. Correspondingly, if we are going to use the ASD or the allowable or the alternate stress design, so we are correspondingly have to use omega sub T is equal to 2 this time. Okay, it's equal to 2 this time. So when we are using ASD, the difference of this is 1.67 and 2. Okay. Okay, so 2 is 0.5. So if we can recall, 1 over 2 is 0.5. Okay, and 1 divided by 1.67 is actually 0.6. So the distance between 0.5 to 0.6 is actually 0.1 or 10%. So when we are using ASD, the estimate clearance between yield strength and ultimate strength is 10%. Take note. I'm sure you know what we are talking about. We are talking about the stress-strain curve of the steel. We already know what is the stress-strain curve. We have what? PIIE. We have the PIIE as an acronym for those points, 5 points. And we are comparing here what? We are comparing yield point and ultimate point. Okay. So the difference of them is 10% when we are talking of ASD and 15% when we are talking of LRMD. Okay. Okay, in the preceding expression, Fy and Fu are specified minimum yield and tensile stresses respectively. So take note of the definition. So Fy is the minimum yield, that is a yield value, but we have to use the minimum one. So there are two extreme on yield. On the graph there is a 2 yield point here and yield point going down. So there are two. They are very close to each other, but still we are going specifically to use minimum. And tensile stresses, and that is the tensile stress, which is if we specify the tensile stress, that is actually the ultimate tensile stress. So that is the reading of the testing equipment when we are testing the tensile strength of the material. That is the reading after it reached the maximum point. Maximum point could be reached. Okay. And notice we are using A sub B, which is the effective area, okay, or effective net area. Okay. So it is very much different from gross area. So effective net area. Okay, this area may be somewhat smaller than the actual net area. Okay, so effective net area may be smaller than the net area because of the stress concentrations and other factors that are discussed in section 3.5. Okay, we will go to that later. Values of Fy and Fu are provided in table 1.1 of this text, table 2-4. Okay, so we already gave you, okay, we already give you example of this table. So in IIEC tabulated specification, we have about 5 to 6 different properties of material that are present. There. Okay. So that is a minimum. Okay. And for tension member consisting of rolled steel sheet, the actual there actually is a third limit state, block shear. So we can solve block shear. We will provide the concept and principle. So that is later on in later section. Okay. So remember, we have block shear. Okay. So what do we have? Technical terms: shear, tension, moment, okay, deflection, okay, bending, flexural, okay, yield, okay, tensile stress, okay, yield, ASD and LRFD. Effective area that could be a little bit smaller than net area. So those are some of the technicalities here. So specifically, let's talk about net areas. Okay, so we don't need to do this very long paragraph. We just need to give you the very important portion here. Okay, the very important portion here. I will show you. Okay, here. Okay, ductile steels are proved to be as much as 1/5 to 1/6 stronger than similar members made from brittle steels with the same strength. Okay, so 1/5 to 1/6. 1/5 is 20%. 1/6 is about 18%, 17 to 18%. So from 17 to 20%, okay, is stronger than similar members. Okay, so we already tackled some concept on ductility and brittle. So brittle is the property much like of a glass. Okay, it could easily be broken. Okay, by presence of, by introduction of stress and the material experiencing a little bit of strain. So just a little bit of strain, if the material breaks, so that is a brittle material. Okay, so take note of that, those concepts, 17 to 20%. Next, important concept. Okay, net cross-sectional area or net area, okay, refers to gross area, okay, minus any holes. Take note, gross area minus any holes. Okay, okay, notches, okay, and other indentation. Those are the possible items that we must subtract from the gross area. So if we subtract that, we will get the net cross-sectional area. In fabricating a structural steel that is to be connected with bolts, okay, the long used practice was to punch hole with the diameter 1/16 inch larger. Take note of this. Okay, it is the long used practice because it is being practiced in actual. We have to reflect this in our computation. Take note, 1/16. What is 1/16? 1.6 mm. 1/16 inches is 1.6 mm. So the diameter of the hole must be 1.6 mm larger than the bolts. Okay, so always plus 1.6. Okay, When this practice was followed, the punching of wool was assumed to damage or even destroy 1/16 more of the surrounding metal. As a result, the diameter of the hole subtracted was 1.8 inch larger than the diameter of the bolt. So 1.8 is 3.2. Okay? 3.2. Okay. So actually, we subtract 3.2, not 1.6. Okay. There is a caveat on that. So for 20 mm bolts, we only subtract 1.6 for 20 mm bolt. For larger bolts, we subtract 3.2. Okay? Okay? So, and actually there are three. There are three. So for small, very small bolts, you have to subtract much less. Okay. For the average bolt is 20. Okay. So that is 1/16, and for 32 mm bolts and above, so we will subtract 3.2. Usually 32 mm and above. Okay. Let's take note of what is the exact application. Okay. These are the secret of the trade that you need to memorize or understand. Okay. 1/16 inches, 1/8 inches. Okay. 1/8 is 3.2. Please confirm in your calculator. What is the equivalent of 1/8 inches in mm? Okay. Today, drills made from very much improved steels enable fabricators to drill very large numbers of bolts without resharpening. As a result, a large proportion of bolt holes are now prepared with numerically controlled drills. Okay? Numerically controlled drills, much in the same manner, CNC. Okay? CNC machine or NC machine or CNC machine. Okay? So, meaning to say, NC machine, numerical control, that is computerized. Okay? That is computerized. Okay? So, though it seems reasonable to add only 1/16 inch to the bolt diameter for such holes, to be consistent, the author adds 1/8 inch for all standard bolt holes mentioned in this text. Okay? Should the holes be slotted as described in Chapter 12, the usual practice is to add 1/16 inch to the actual width of the hole. Okay, that is for slotted holes. This author, okay, this author, meaning, who is this author? This is McCormack Chernak. Okay, please confirm. McCormack Chernak. Okay, so McCormack and Chernak, in this book, used 1/16. Rather 1/8. 1/8. 1/8 is actually equal to 3.175 according to Joshua, and therefore that is equal to 3.2. That is 3.2 mm. So thank you, Josh. So that is, please take note in your notebook or memorize it. If you don't want to memorize it right now, please take it note in your notebook. Okay, not scratch paper. This is very important to be placed on a scratch paper. This is a notebook material. Okay, so, and because of that, we could either use 1/16 and 1/8 depending upon the problem. But if this author did not specify in the problem, we will use 1/8. Take note of that. Take note of that. But if I use a problem solving practice from another book, okay, it may use 1/16. Take note of that. So that's why it's better to ask, sir, Are we using the problem from McCormack-Chernak or not? So you can confirm. You can confirm. Okay. For steel much thicker than bolt diameter, it is difficult to punch out the holes to the full sizes required without excessive deformation of the surrounding material. These holes may be sub-punched with diameters 3/16 inch undersized, and then rimmed out to full size after the pieces are assembled. Very little material. So it is undersized, right, by 3/16. Okay, undersized. Okay, for bigger holes. Okay. So that is where it is being applied. For steel much thicker. So meaning to say, if the thickness of the plate of the material is larger, if the thickness of the material is larger than the diameter of the bolt, okay, so we will use 3/16 undersized, but it will be rimmed out to full size after the pieces are assembled. Very little material is damaged by this quite expensive process, as the holes are even and smooth, and it is considered unnecessary to subtract 1/16 inch for damage to the sides. Okay. Unnecessary. We will not add, we will not plus 1.6 mm. We will not plus 1.6. If the thickness of the plate or the material is larger than the diameter. Ignore that. No. Okay? It may be necessary to have even greater latitude in meeting dimensional tolerances during erection, and for high-strength bolts larger than 5/8 inch in diameter. Okay? So for high-strength bolts larger than 5/8 inch diameter, can you compute? Okay? Let us show our calculator here. So calculator, let us show you. Okay, Casio calculator. So where's the Casio calculator? So I will open a Casio calculator. So let's find out. Where's the why? It is not showing. So where is the Casio calculator? There. Okay. So now you are now seeing the Casio calculator. So let us compute 3. What is that? 3 or 5/8. Okay. So 25.4 times 5 divided by 8. So this is in mm. So this is 15 or 16. So 16 mm. 16 mm bolt. So for 16 mm bolt, okay, that is high strength. Okay. So we'll have what? Greater latitude in meeting these tolerances. For such a situation, holes larger than the standard ones may be used without reducing the performance of the connection. These oversized holes can be short slatted or long slatted as described in section 12.9. So later on we will do that. So right now we will take a look at an example, okay, so that we can let's take a look at example. So let us turn up the calculator. Okay, so we have example. Let us turn up our video. So example number 1. For tension members, determine the net area of the 3/8, okay, 3/8 inches by 8-inch plate shown in figure 3.2. Okay, so the size of the plate is given. So 3/8 inch, meaning that is the thickness of the plate, okay, and 8-inch is the width of the plate, okay, that is the width of the plate. So meaning to say, if you measure this this width from this point to this point, this is 8 inches. Understood? Do you follow? And if you measure the thickness of this is 3/8 inches. So 3/8 by 8 inches, right? But that is what we mean by plate. PL means plate. Okay? You can use that into your what? Into your engineering plan. PL 3/8 by 8, or in terms of mm, that is what? PL 16 by what is 8? 200. So 8 is 200. So PL 16 by 200. That means 16 mm by 200 mm. Okay? Okay. If you are using what? SI unit. Okay? So let us find out the net area of this. So let us make this as the free body diagram. Cut this off. Cut this portion off. Free body diagram. We have what? P sub U, P sub U. That means ultimate force, or tensile force. Ultimate tensile force. Okay? So we are actually using the term tensile force. Okay? Okay? Or tension. Just the word tension. It means the force. Tension. Okay? So, tension, P sub U, tension, P sub U. So, we are in equilibrium. Now, if you look at the side view, so P sub U, the P sub U here is actually represented in these two smaller or thinner plates. So P sub U, there are 2.5 P sub U. 0.5 plus 0.5, that is 1 P sub U. Okay? Okay? So that is how it is being represented here. So it is still equilibrium. What is the dimension of this plate? The thickness is 1/4 and the width is 8 inches. So again, 1/4 by 8 plate. Okay? As you can see, there are 8 balls, but in the side view, we can only see 4 because they are aligned. They are aligned horizontally and aligned vertically. Right? So, okay. So, let us find out the area. Let's find out the area. So, if that is the area, if that is the given problem, therefore, the area is net area. Okay. How can we compute the net area? Net area is equal to 3/8 inch times 8. Okay. This is the gross area. This is what we mean by gross area. So if you multiply this with this one, that is the gross area. Okay? So thickness times width, that is the gross area. Actually, that is cross-sectional area. Okay? Gross cross-sectional area. If you cut this off here, you will see 8 inch and 3/8 inch. Okay? So therefore, if you multiply, that is the gross area. So this one is the gross area. So gross area, according to the previous paragraph, we need to subtract all the holes. Right? If we say all the holes, we only subtract the holes on that particular line. This is our line of cross-section. This is cross-sectional lines. Right? This is the cross-sectional line. Why? Because these are the cross-sectional lines that would support. The cross-sectional lines is the line that cuts off that cross-section, and that cross-section which cut off is the area which would support the resistance to failure. Okay? So that's why we are only subtracting 2, because there are only 2 bolts in a single line of cross-sectional area. Okay? There are only 2. Okay. So one line, one line, one line, one line. So there are 4 lines of weakest point. So there are 4 lines of weakest point. There are 4 weakest points here. 4 weakest lines actually. So let us correct ourselves and let us make it accurate expression as possible. There are 4 weakest lines of cross-sectional area. So this is the weakest line. So this cross-sectional area is strong because there are no holes. This actually we don't involve this plate, the upper plate and the lower plate. We only involve this plate because of the question. The question is determine the net area of that plate 3/8 by 8. So this is the plate 3/8 by 8. We are not being asked what is the same question for 1/4 by 8. We are not being asked of that. We are being asked for the 3/8 by 8. So we are only considering this part from this point to this point, and not this point, not the thinner plate, the thicker plate in the middle. Okay? Right? So that is the weakest line. This is the weakest line number 2, weakest line number 3, and weakest line number 4. And you will notice these weakest lines have the same amount of holes. There are 2 holes per line. If you compare that to this line, if I draw an arbitrary line here, it is stronger because there are no holes. Okay? So therefore, we have to make sure that this weakest point, weakest line, would be able or must be enough to support resistance to failure. Okay? That is what we are talking about. Therefore, we only need to subtract 2. This means this 2 minus 2. So there are 2 holes per weakest line. And what is this? What is this value? This is 3/4 inch plus 1/8 inch. 1/8 is 3.2. This is, take note, this is being used by this author. In some author, 1.6 mm is being used. 3.2, this is equal to 3.2. 1/8 is 3.2. Other authors will use 1, but the same explanation, only different usage. Okay? Only different usage. Which is right? Which is wrong? They are both correct. Because it depends on the engineer. Okay? 1 over 16 is possible, 1 over 8 is possible. That is according to the concept. Okay? That is according to the concept. 0. 0 or plus 0 is okay. Plus 1.6, okay. Plus 3.2. It depends upon the condition. There is a condition for each and every amount of what? Allowance to the whole. Okay. So, meaning to say, 3/4 is the size of the bolt. That is the diameter of the bolt. How do I know that this is the bolt diameter? Here in the given 3/4 inch bolt, there is a given. So the bolt is 3/4 inch and I would need to add 3.2. Usually, in board exam, 3.2 and 1.6 are being used, but if I can still recall, most of my practice I encountered 1.6 more than I encountered 3.2. I encountered 1.6 more in the board exam, okay, rather than 3.2. Okay, so give me 1 minute. I will just connect my device to power supply. Okay, let us resume. Any question? Any question? Well, okay. So let's continue. So we have gross area minus the diameter of the hole. This is the diameter of the hole times the thickness. Okay, diameter times the thickness. This is the area punch out. Okay, this is the area punch out. That is the largest projection of the hole, okay, in the metal plate. Okay, then times 2, meaning 2 holes. Okay, because there are only 4 specific weakest line. The weakest line will actually start from the edge, going to the nearest point of the hole, then along the hole, then from this point going to the nearest point of the neighboring hole, and then from the nearest point of the hole to the edge. That is specific. Why I have to say that? Because this is another example of a line which is not the weakest link. Okay? This is not the weakest line. Okay? Cracking it or fracturing this material, fracturing it like this, from the edge going to the tip of the hole, here, the tip of the hole, and going here to the another tip of the hole and to that point, to the edge. Okay? That is not the weakest line. Actually, if that line just barely touches the hole, then it is equivalent to the cross-sectional area of this. And that is not the weakest. That is the maximum resistance of the material. Okay? Take note of that. Take note of that. Of how can we draw the weakest line. Take note of that. So, meaning to say, gross minus the number of holes that must be subtracted to be able for this cross-section to be the weakest line, and then that must be equal to the net area. That is the net area. Okay? So the answer now is 2.34 square inches. Okay? Of net area. Any question? Any question from that example? So let us take a look at this. Lining up centroidal axis of members. So centroidal axis. Okay. So lining up centroidal axis of members. So meaning to say, this is the centroidal axis. Okay, you notice the center line, another center line. Note at this center line there are no holes, but in the center line there are plenty of holes. Okay, okay. So that is what we call gauge line. That is where, if that is a centroidal axis, that is where we usually base our holes or computation or placement of holes. Okay, line passes through center of gravity of its bolt group. Okay. Oh, this one, no? Passing through the center of the bolts. Okay, up to this point. Okay, another gauge line, but this gauge line did not pass through any bolt. Okay, okay. So what do we mean by this? 2LS, two angles. Okay, so there are two angles, meaning to say 2LS meaning two angles. How to read this one? Angle. L meaning angle. With S, angles. So two angles. Two angles. That is how to read this. Okay? Okay? So that is how you will put that on the drawing and how to read it. And we know what do we mean by angles. Okay? So we already know what do we mean by angles. Just the importance of eccentricity. Okay, so there are eccentricity that we must understand. So you notice. So this centroidal axis coincide with usually that is not the case. Okay? Usually like this. So staggered holes. These are staggered holes and it doesn't coincide with the center line. Okay, so that is usually the case. Okay. But if this is the vertical part of the truss member, vertical truss member, usually it is located center. Okay, center line. Okay, and again we will cut this off and have the next topic in the next live stream just right after this, in order for our videos to be maintained at shorter amount of minutes, right? So that our videos is shorter. It is very hard to study. It is very boring to study it. If all of the lectures are 1 hour, 2 hours, 1.5 hours, so let us cut each and every video shorter. So going to the next topic, so we'll cut it right here. And before we do that, I will give you 10 to 15 seconds chance to ask questions so that we may be able to go to the next topic. Any questions? So I think there's none. So again, this is Dr. AP, Preaching Engineering for Nation Building. See you on the next live stream. Just right after this.